Thank you. Yeah, thanks again to Martin and Jamie for having me here and for you to drop by. I know that there is a fierce competition this afternoon. I'm going to be talking about the issue of singularity resolution and sort of focus on the black hole singularities and in a particular regime, just because the issue of singularity resolution is, of course, large and concerns many sort of different cases. And of course, a lot of work has been done on cosmological cases. And I think quite a lot of recent interesting work has also been done when it comes to the black hole singularity resolution that we sort of people interested in foundations of physics should be aware of. Given this audience, I will be totally unsurprised if actually many of you are already aware of all, or at least most of the results I will be talking about today. And so in that case, I just wish to remind you of what Jeremy Butterfield calls the Fermi's pleasure principle of never underestimating the pleasure the audience gets from being told what they are already familiar with. I should also add that quite a bit of this may overlap with the material that Eric Curiel gave in a recent talk. And this is a result of sort of independent convergence on basically reading similar papers. I should also add that, of course, Eric's version of the take on this is probably superior to mine. Okay, so this is the plan. I'm going to start with some general remarks about singularity resolution and what it may mean, and then go very briefly through Penrose's 1965 singularity theorem and go through sort of three possible responses. And I think what's interesting in those responses is that they sort of very natural and have recently been shown to, well, not work that great. Let me begin with some general things about singularity resolutions. Of course, the issue of singularity resolution seems to motivate, to a certain extent, research in quantum gravity, simply because general relativity predicts occurrence of singular spacetime, of spacetime singularities, if you wish, in their many distinct and subtle forms, and under the sort of large class of circumstances. And I think from a philosophical point of view, it's interesting to know what could or should be meant by the phrase singularity resolution. And in particular, we should, or at least may wish to sort of have a clear idea about what could make some approach to a singularity resolution successful. And moreover, it would be good to know if a resolution happens, then in what regimes and at what costs does it happen? That is sort of which physical principle which seemed to hold classically would have to fail at some higher energies for this singularity resolution to work. And this, of course, also raises interesting questions about intertheoretic relations, because we would have singular models arising as some sort of classical limits of non-singular ones. And that's interesting on its own. What I want to do in this talk is to observe that there are quite a few recent results which are of relevance, and I think it may be useful to sort of survey them, because it seems that a sort of clear picture concerning the fate of black hole singularities in semi-classical gravity begins to emerge, or at least if we help ourselves to sort of some quantum field theoretic techniques, which unfortunately are mostly, well, non-interacting fields, but nevertheless, a sort of clear picture begins to emerge. And the picture is that although there may be singularity resolution somewhere deep down there at the Planck scale or something like that. It doesn't seem to happen in quantum field theory in curved spacetime or semi-classical gravity. And there is nothing sort of technically new in this talk. This is a sort of, work in progress talk and a small group of friends. It's probably too early for lunch for some of you, but feel free to treat it as such, as a lunch talk, so to speak. Good. So in this talk, I'm only interested in black hole singularities and in sort of, so to speak, intermediate extrapolations from GR. That is quantum field theory in curved spacetime, where we sort of, well, not sort of, we exactly treat the background spacetime structure as field and are interested in the behavior of QFT over that background, and semi-classical gravity, that is the project of solving the semi-classical Einstein field equations, so sort of including small corrections due to quantum effects by swapping the classical stress energy tensor with the expectation value of the suitable operator. So why could or should we be interested in this sort of regime? After all, many philosophers of science sort of jump to the full quantum gravity and ask questions about that, because that well, can be seen as both most exciting and the most fundamental. Well, I think there are at least three reasons to sort of look at those intermediate extrapolations. The first is that, well, there are many orders of magnitude before the Planck scale, so many proposals about what happens there, but so little evidence to guide us. And so sort of intermediate theories, the quantum field theory in spacetime or semi-classical gravity, may be seen to be sort of more conservative or less speculative. And therefore, one may also think that some problems and questions seem to be better defined in the context of those approaches. And moreover, one could say that in a way, they already do account for some of the quantum effects, which could in principle be used to resolve singularities. So sort of inherent interest to have a look at them. And also these extrapolations seem, well, a tiny bit less complicated than what happens in full quantum gravity theory. And I will come back to that thread in a moment. Good. So just so we are all on the same page, let me remind you about the Penrose's 1965 theorem. And again, Butterfield Fermi pleasure principle holds. So Penrose's singularity theorem shows that if a spacetime which has a closed trapped surface satisfies the null energy condition and has a non-compact Cauchy hypersurface, is future null geodesically incomplete. And this singularity theorem is, of course, of the relevance when it comes to situations such as gravitational collapse, because we can expect to see a closed trapped surface to arise in that context. And indeed, from Christodoulou and subsequent heavy and hard work in mathematical relativity, it is known that trapped surfaces can form dynamically. The null energy condition seems to be a reasonable classical sort of restriction on how matter behaves. The causal condition is just there to sort of make sure that we have good control over physics in that regime. But if so, well, then we have singularity in the sense that we have at least one inextendable and incomplete null geodesics. And many people see that as a sort of breakdown of the predictivity of the theory, because sort of for a system moving alongside geodesic, it will cease to exist in a finite amount of time, or we will not know what happens to it for all possible values mm, of the, well, not the time parameter, but the affine parameter. And so if one wants to avoid the singularity theorem, of course, one needs to have some effects violating one or the other of the premises of the theorem. So here's Boževal's nice discussion of singularity resolution. This is mostly done in the, well, this is done exclusively in the quantum cosmological context, but I think those points are sort of worth bringing back. So Boževal says that the main problem posed by a singularity is the breakdown of dynamical equations at such a point. We may sort of frown at the talk about singular points, but let's be charitable and assume we sort of we are okay with this. And so then Boževal says, in any complete discussion of quantum removal of classical singularities, one thus has to address 3 points. First, one has to isolate potential singularities, that is, find conditions under which singularities must occur for the classical equations. And of course, by the sort of premises of the Penrose's 1965 theorem do exactly that for a sort of wide range of circumstances in classical GR. One then, Boževal continues, has to determine the quantum evolution equations for the dynamics around those classically singular states. So maybe it's sort of classical on-shell states that are singular, but off-shell states would not be singular or would be less singular, and sort of the other states would sort of dominate in the gravitational path integral or something like that. And finally, the dynamics has to be shown to not to break down when quantum behavior is taken into account. Okay, so far so good. Boževal then notes, however, that all of the 3 steps, even the first purely classical one, are too complicated to approach in full generality, but can be dealt with in symmetric models, which classically also show a wealth of different singularities. In the quantum cosmological context, a lot of the focus is on having curvature-like quantities behaving appropriately nicely, so being bounded because curvature diverges at, for instance, the Big Bang singularity. And so what often happens in those contexts is that one is not really concerned so much with the premises of something like a singularity theorem, because the sort of full scope of situations covered by a singularity theorem is too complicated to deal with, and one only looks at some simple, highly symmetric models. And so some of us may feel uneasy at this stage, because if my singularity resolution only works for some exact solution, then how good is it really? Taking an exact solution and calculating some corrections which remove singularity of that solution, that may be perhaps a sort of promising proof of principle, but it's not a sufficient evidence that similar corrections will work for a whole generic class of spacetimes and circumstances. And even if it turns out that various systems end in the same end states, for instance, by Birkhoff theorem or by the final state conjecture in the context of gravitational collapse to a black hole, one would like to know where and which premise of the theorem becomes unreliable if the singularity is to be sort of healed or resolved. And I think this complaint could be raised against many models. For instance, the black to white hole transitions, see Malaferina's paper for still relatively recent, nice overview, are done almost exclusively for spherically symmetric cases. And so a sort of wide applicability of those models is really an open question, if you wish. Here's a sort of another way of, I think, not the most promising way of going about avoiding a singularity theorem. And a friend who shall remain anonymous used this argument against, well, in a discussion of related issues. So I think it's a sort of genuine sentiment that people have, and it's a true friend, a real person, not a sort of fictional entity of mine. Okay, so the argument goes, well, but the singularity theorem uses spatio-temporal notions, and in quantum gravity, we should not expect those notions to be applicable. And I think I want to say two things about this sort of sentiment. A, this assumes some of the very particular approaches to quantum gravity, because it seems that there is a sense in which, in something like asymptotic safety or holography-based approaches, we do not have some drastic loss of spatio-temporal notions. And second of all, this does not specify which of the premises of the theorem has to go. Do all of them have to go to sort of simultaneously? And how to sort of see that from this fundamental non-spatio-temporal regime, what we get in, I don't know, semi-classical or classical remit, that thing violates premise of the theorem, and if so, which one? And again, I think this is mostly pointed out, what happens, for instance, the black to white hole transitions is only pointed out in specific highly symmetric model where what basically happens is that the Einstein's field equations are widely violated. So this way, I think there may be something to this sentiment, but it really, a lot of work would be needed on the side of my anonymous friend to show that something like that actually makes sense. And well, all of this so far ignores the fact that Penrose's 1965 theorem is perhaps not the last word, and indeed it has been generalized to cover various interesting cases. And so now I want to cover, well, two such cases and then discuss a sort of response which does not directly attack any of the premises of the theorem, but sort of the whole conceptual setup of the theorem, so to speak. And so I want to talk about energy conditions, then causality conditions, and then about the choice of probes relevant in the context of the singularity resolution. So the theorem, as we have seen it before, relies on the pointwise null energy condition, which states that the Ricci curvature is non-negative when contracted with any null vector. But the null energy condition can be violated, even classically, by massive Klein-Gordon field or by non-minimally coupled scalar fields. And it can, of course, be wildly violated in various quantum field theoretic scenarios. So in a way, this is great. For instance, the sort of proliferating family of the regular non-singular black hole solutions, which look asymptotically flat from the exterior, have some forms of horizons, but do not have central singularities, rely on the violation of the energy conditions, including the null energy condition, because for them to be non-singular, they have to somehow avoid Penrose's 65 theorem. And there is a lot of recent work which seems to show that there are some formation mechanisms for regular black holes and evaporation mechanisms for regular black holes, and that they can have either asymptotically de Sitter cores or asymptotically Minkowski cores. And for de Sitter, there are a few different families of solutions, and there are also other ways. There is various sort of deformation techniques that one or other methods to construct such solutions. And all of them violate, at least all of the known ones, violate the null energy condition, as far as I know. But in a recent paper, Frey-Vogel and their collaborators recently proposed another condition, what they called a smeared null energy condition, so SNEC, which is the requirement that average of energy over a null geodesic of some fixed length is bounded by this equation where Gn is the Newton constant. And have a look at that paper if you want to sort of see a fully fleshed out version of this requirement. So what's interesting about the smeared null energy condition is that one can show, as Frey-Vogel and their co-authors do, that it reduces to the average null energy condition when region over which the average is taken is large. It can be derived from a Lorentz invariant quantum field theory and can be used to establish null geodesic incompleteness using techniques established by Fester and Conteau in a recent paper. So what Fester and Conteau do in that paper is they say, well, various energy conditions that includes Penrose type, various singularity theorems, which includes Penrose type singularity theorem, but also Hawking-Penrose cosmological singularity theorems rely on various energy conditions. Those are violated, but perhaps they could be rederived using bounded violations of those energy conditions. For instance, average conditions, well, that we already know that can be done, but also negative but not too negatively large states which arise in certain quantum field theories. And so it turns out that this smeared null energy condition can be used to derive Penrose type theorem. And so if one's reply to the theorem is that, well, it relies on an energy condition which is violated, well, hold on. Perhaps the violation for physical reasons, such as particular QFT we're interested in, is only so large, and then the theorem could be, so to speak, rederived. And so violation of an energy condition does not have to be automatically a sort of successful way of eliminating the singularity. Here's another interesting recent result. So Arthur Wall showed that we can still prove Penrose type theorem and conclude that the spacetime is null geodesically incomplete if we replace the null energy condition with two other requirements: existence of what Wall calls quantum trapped surface, so a null surface where entropy decreases to the future, as we may expect in gravitational collapse, and a generalized second law, which is basically the statement that for two special sizes and for any future causal horizon of some observer, the generalized entropy, which is normal entropy of whatever matter we have plus the entropy of the relevant horizon, for instance, motivated by the black hole thermodynamics, satisfies this inequality that obviously we can call a generalized second law. And it turns out that the null energy condition can be replaced with this other, with these requirements, and a Penrose type theorem can be proven from those assumptions. Okay, well, so maybe we would need to have very large violations of the null energy condition and or violations of the generalized second law that may not be looking so promising. So let's switch to sort of another argumentative strategy. Penrose 65 theorem relied also on causal assumptions. Perhaps those assumptions have to go. And what I'm just going to do now is quote two passages from a recent absolutely beautiful paper by Ettore Minguzzi, who looks at sort of recent discussion about the black hole evaporation and the sort of causal structure of fully evaporating black hole that actually Martin significantly contributed to. And this is Minguzzi's dialectic. When we think about gravitational collapse and semi-classical evaporation, we are in the presence of a loophole argument. I'm just going to read this because I think Minguzzi put this nicer than I could have. It's such a beautiful paper. So the loophole is this. In order to infer the formation of singularities per Penrose's 1965 theorem, we need to assume global hyperbolicity. But unfortunately, one would expect the formation of a black hole, and hence its very evaporation, because we are also allowing for semi-classical effects. And if so, then the global assumption of global hyperbolicity could not have been satisfied in the first place, because fully evaporating black holes are not globally hyperbolic. As a matter of fact, they're not past reflecting. In other words, the hypothesis of Penrose's theorem seemed too strong for a realistic universe. As taken into account the quantum effects, it appears that the existence of black holes implies a certain amount of unpredictability. And so these observations open the possibility that trapped surfaces do not necessarily imply the formation of singularities, at least when quantum effects are taken into account. And so I think this is a good worry. It's a serious worry. And what then Minguzzi does in this paper is show that causal assumptions in the Penrose's theorem can be relaxed. And this is Minguzzi's conclusion. In Penrose's singularity theorem, we have two conditions. Spacetime is globally hyperbolic, and there's a non-compact Cauchy surface, and they can be weakened to spacetime being past reflecting and the spacetime being spatially open. I might have used wrong direction of reflectivity in the past slide. Well, if so, it's on the record, and I'm an idiot. Anyway, Minguzzi continues, by dropping the global hyperbolicity condition, we have shown that determinism is not necessary in order to infer that trapped surfaces lead to spacetime singularity. And the classical picture of gravitational collapse is therefore consistent with that of quantum field theory on curved background, where we would have to renounce global hyperbolicity anyway due to black hole evaporation. And so some of the tension between quantum field theory and GR is resolved by showing that we can have coherent description of both formation and evaporation and the overall non-globally hyperbolic spacetime structure. And so in this sense, saying that, well, Penrose's theorem relies on causal conditions, maybe those are the culprit, and the sort of singularity resolution strategy should go by saying those conditions are inappropriate somehow when it comes to occurrence of singularities. That line of reasoning still could work, but we would have to attack much weaker causal conditions. I think one could ask an interesting additional question here, and I'm just going to ask it. I don't know what the answer is, but hopefully at some point we'll know. So various people, including Kay and Fester and Higuchi, and of course see John Ehrman's work for a sort of clear statement about why we should care, ask whether, and if so, which non-globally hyperbolic spacetime can be used as a good background for quantum field theory. And so what they do is they work with a QFT for the Klein-Gordon equation. So they construct a star algebra which is nice enough and satisfies the Klein-Gordon field equations, and to quantize it at canonical commutation relations for the appropriate smear test functions. This procedure works for any globally hyperbolic spacetime, and so is also appropriate for certain sort of judiciously chosen neighborhoods of any point in a non-globally hyperbolic spacetime, simply because we can always find a small enough neighborhood of any point where we do have global hyperbolicity. And so in those global hyperbolic neighborhoods, we can always construct these sort of local star algebras. And then one can ask whether they form a sort of global algebra with the natural net properties. For instance, if U is a subset of V, then A of U is a subalgebra of AV. And if so, those spacetimes are said to be quantum compatible because they sort of, despite their lack of global hyperbolicity, allow for a sort of globally well-defined quantum field theory in certain minimal algebraic sense. And it turns out that some spacetime, non-globally hyperbolic spacetime, for instance, time-like compactified Minkowski, are quantum compatible, and some others, for instance, Misner spacetimes, are not. So I think it's a good question now that we know so much more about causal structure of fully evaporating black hole spacetimes. We could ask whether that non-globally hyperbolic spacetime is quantum compatible in this or similar sense. And if it turns out to be quantum compatible, then I think that's sort of another way in which some of the tension between evaporation and classical dynamics could be seen as disappearing. Okay, here's a sort of third possible response to a Penrose type singularity theorems, and that concerns choice of probe telling me whether a singularity exists in spacetime. Now, this is not so directly relevant to Penrose type theorem as previous to sort of hypothetical attempts, because the results I will be talking about are not about null incompleteness, but about time-like incompleteness in static or stationary spacetimes. But I think it's interesting because it sort of shows us that we could try to find a way around the Penrose's singularity theorem without explicitly denying one of the premises, or at least it seems so, but by sort of switching the conceptual setup, if you wish. And then it turns out that this way of addressing the theorem for time-like cases doesn't seem to work that great either. So what's the idea? Well, the idea goes back to Horowitz and Morolov paper from mid-90s. And they point out that, well, maybe geodesics, because geodesics are paths of classical test particles, are not the best probes when searching for singularities. Perhaps we should look at something like quantum wave packets and ask whether the quantum wave packets can see the singularity. And the wave packets are, again, often, although not always, but often and typically Klein-Gordon operators because they're the easiest to work with, and are seen as non-singular if evolution of any state is uniquely defined. In other words, if the evolution operator of a free particle is essentially self-adjoint. And so one could think, well, okay, this is an interesting proposal because instead of working with classical test particles, we're now working with something quantum, and well, maybe some things will change. And they change. It turns out that there are geodesically incomplete spacetimes where this operator is essentially self-adjoint, and so the natural interpretation of this is that the quantum probe cannot see this classical singularity. But there are also geodesically complete spacetimes where the operator is not essentially self-adjoint. And again, Juliusz has a beautiful discussion of sort of issues concerning determinism and essential self-adjointness. And recently, Konkowski and their collaborators were able to show that essential self-adjointness fails for a particular class of spacetimes that have been used for quite a while to study scalar field gravitational collapse, and that this criterion also fails for overspin current naked singularity. And so this means that these forms of singularities cannot be sort of removed or ignored if we switch to such quantum wave packets. And so again, let me emphasize this does not directly concern the Penrose's 65 theorem, because now we're talking about exclusively about time-like singularities, and these evolution operators are are well defined in statico-stationary spacetimes, not in general cases. But it seems that this sort of way of thinking about singularity resolution when we switch from geodesics to some other class of probes does not have sort of the best prospects, at least in general cases. It seems to be working in some cases, but it doesn't. It seems to be also not working in a wide range of other cases. Okay, that's it. I'm at the end. So what's the right conclusion to draw out of this? Well, to me, it seems that many natural ways of avoiding Penrose's theorem are blocked, at least in the sort of quantum field theory on curved background or semi-classical gravity regimes. And so insofar as we're sort of basing our expectations about occurrence of space-time singularities on those theories, we, I think, have every right to expect them to show up in this intermediate regime on the way to the Planck scale as well. And so another question one could ask, and this is the question I'm just going to leave us with, is, so what would be the strongest available Penrose type theorem? Well, it seems that we would need a theorem that is based on either something like quantum energy inequality or the smeared null energy condition, or a generalized second law, and use Minguzzi's weak causal assumptions, and possibly also allow for existence of ichronal regions in the interior, as does Martin's recent singularity theorem. The last thing, I think, would be rather unlikely to be achievable with the generalized second law, because Wall uses generalized second law to prove a no-go theorem about time machines. And so in a way, we would have sort of two strongest available Penrose type theorems, assuming that those techniques are sort of modular enough, and we can kind of swap the energy condition part of one derivation and plug it into another. And I think this can be done. And if so, then I would say that this situation makes sort of puts strong restrictions on available strategies for a singularity resolution, at least in the context of those intermediate physical regimes. Yeah, that's everything I have for today. Just a few slides with the references if anyone is interested. Thank you so much.
That's really nice, Juliusz. Thank you. Thank you very much, Juliusz. It was a lovely talk.
Maybe I'll stop sharing the screen. And
Sure, if you like.
yeah. Oops.
Okay, well, do we have any questions? Yes, Dan?
Yes, hi. Well, first of all, thank you for the talk. I actually had some comment because you discussed whether quantum field theories exist on evaporation spacetimes. Now, it happens to be something I have been working on recently. So,
perfect.
So actually, also under Klaas Landsman, who's also in this seminar, I see. So, so perhaps we could talk about that sometime. But the issue is, but what I would like to say is that the issue is not so much whether a quantum field theory on the spacetime exists in the first place, because an F-local quantum field theory, in the sense that K and Fuster and Higuchi discussed, you can always construct on strongly causal spacetimes. But the more important question is actually whether the spacetime admits physically sensible states, in particular Hadamard states. So for the black hole evaporation spacetime, the problem is that if you start with a Hadamard state, so one where you can actually define the stress energy tensor, then it is not entirely clear if for instance, the stress energy tensor does not blow up as you approach the Cauchy horizon. And it seems that you cannot tell whether this is the case from just the causal structure, but you need more information about the actual geometry, for which you would actually need to solve semi-classical Einstein equations, which, well, is a whole other story. And then I had a second question about using different probes. You mentioned that if you go to quantum fields, you not really need geodesics anymore. So that might be sort of be a way to resolve the singularities. But if you think of Klein-Gordon fields in quantum field theory, you sort of get null geodesics from that, from the dynamics of those fields, namely from the way the singularities of the two-point functions propagate. And I was wondering if in that sense, sort of using quantum fields as a probe doesn't just bring you back into the sort of classical situation, but I don't know how to make that precise, really. I was wondering if you have any thoughts on that.
I don't have any thoughts on that, but given that there are these other results about geodesically complete spacetimes where we have failure of self-adjointness, it seems that those things are kind of independent from each other. But I wish I could give you a better answer. Oh. And I would also love to talk more about these topics with you in possibly class at some time.
Perhaps we can exchange some contact details later.
Yeah, totally.
Ramesh?
Yeah, Juliusz, that was very nice. I had just one thought on the first classical argument you were talking about, namely, if I can resolve the singularity in a particular high symmetry case, does it mean anything or not? And you mentioned in particular that, for instance, the spherically symmetric black hole collapse, you can stitch it onto a white hole and somehow resolve the singularity, right? So let's say somebody has successfully done that. So the question is, does that mean anything? Does it mean that we can therefore generalize most other singularities through some such stitching process or not? So the thought I had was the following. Let's go back to pre-Penrose. We knew Like Oppenheimer and Snyder showed, you can collapse a dust cloud and make a Schwarzschild black hole from spherically symmetric initial conditions with a horrible singularity and all that, right?
Right.
And then people hoped for decades that, oh, that's a very special situation, spherically symmetric. The moment I break the spherical symmetry, these dust particles are going to miss each other. They are no longer going to collapse into a single point. So, probably there's no singularity at all. Or if at all, it will be a kind of a weaker kind of something. Okay. And so, that was the hope for a lot of people until Penrose came and showed, look, it doesn't matter. If you give me these very generic conditions, initial conditions, and you give me Raj-Choudhury's equation and the appropriate energy condition, it's going to always have geodesic incompleteness, right? So the way I look at that story is to say, the spherically symmetric gives me a horribly strong singularity. I can weaken it. I can weaken it by reducing the symmetry, but it will still not be, it doesn't go away. There is still something left over. That's Penrose's story. Okay.
Yeah.
So if I just translate all this now to the stitching and evaporation or other white hole thing, the way I look at it is, if you can eliminate the strongest of them all, the Schwarzschild singularity, I presume it's a Schwarzschild singularity. Actually, I don't know what this black hole to white hole you're talking about is, but assuming that you're doing it for a spherically symmetric case, then I would have said it should only be easier to eliminate the other singularities, which are all weaker anyway. They're Cauchy surfaces, something like a Kretschmann scalar probably is not as singular for these other guys as for Schwarzschild. So that first line of attack to me seems promising. You can do it in one case, and if you can believe that solution, as you said, you have to violate the Einstein's equations over some little region. Let's say you accept that. Then it seems to me that very likely we can resolve all singularities. By analogy, I'm just arguing by analogy.
Yeah, good. I think there's a sense in which I totally agree with you, namely, doing something like that in a spherically symmetric case is an interesting proof of principle. That this, in principle, could be done at least for certain types of system. But for instance, when we do it using surgery techniques, like they do it in the black to white hole transitions, as far as I know, there is no known way of doing that if we have even just a little of spin. And so it may be that a sort of technique that I use to stitch those solutions may not sort of obviously or easily or perhaps at all generalize to other cases.
I get the point. Yeah. Okay. The technique won't necessarily work, but I still say
at least I have no guarantee that it will work.
Agreed.
And so I would need to see more. Yeah.
Yeah. Okay. But if you can solve the worst case, the others ought to be easier. Maybe you need a different technique. Okay. But anyway, I have said my piece.
I think on this point, if I may make make a comment on this point. Let's take Kerr. Right now, in Kerr, we have a Cauchy horizon, which is the manifestation of the incompleteness in Penrose's theorem. Because in Penrose's theorem, the assumption is global hyperbolicity, and as soon as you leave the Cauchy horizon, you're no longer in that region. And so the incompleteness there just comes from a geodesic leaving the development of the initial data. Now, Minguzzi says, actually, we can prove using either past or future reflectivity, the singularity theorem. And the kinds of singular geodesics that you get from that are still not the incomplete geodesics of the Kerr space-time. And that's the remarkable thing. There are incomplete geodesics in Kerr in the interior that are not because they leave the development. They are because they actually hit a ring singularity in the middle of the black hole, as it were, in the interior. So Ramesh is saying, well, Schwarzschild has a bad singularity in a certain sense, but Kerr supposedly say, for instance, it only has a little ring singularity, and the only incomplete geodesics are one that travel in a particular direction. So, perhaps we can resolve those singularities without too much trouble. That's, I think, a totally fair point. But then the worry is this. Within the class of spherically symmetric models, you can somehow perturb these model solutions and the cloud collapse, etc., and produce a picture where you still expect there to be a strong singularity, like the Schwarzschild one. But when you're in the spinning case, when you're in the Kerr case, and you start perturbing the initial data, then the picture of what the singularities look like is no longer at all something that's understood. So for instance, we don't know if when you perturb the Kerr interior, what you end up getting is a bad singularity, almost as bad as Schwarzschild, or if you just get a Cauchy horizon. And then the ring singularity might change a little bit, but we don't know how it changes. So for me, the main question here really is just, what do the singularities look like inside a rotating generic black hole, right? And that is something we have no idea about, right? That's the main question, right, for me, and in the direction of Ramesh's point, because they could be terrible. We don't know.
Okay, so Martin, yeah, no, you're absolutely right. Since we don't know what they are, as you said, they may be even worse than the Schwarzschild singularity. I was just starting with this mindset that it only gets easier as you break the symmetry. But yeah, you're right. We have to first solve the complete structure of the generic singularity from generic initial conditions, and then figure out how to solve it. Yeah.
And so from that perspective, it would be really great if we had some simple effect like violation of a energy condition on the way there that would sort of make the whole question sort of much easier, because they would not form at all in the first place. But that doesn't seem to be the case, at least in certain regimes.
Wait, what do you mean? We can just consider vacuum here.
Oh, I just meant something like, the claim that certain types of QFT violate the null energy condition.
Yeah.
And so that as a way sort of around the theorem, and say they do not even begin to form. Well, they begin to form but do not form because we have this additional
yeah.
effect.
But I think you can study. I think the question's interesting at all levels. Like you can think about it from the energy perspective. You can think about it from the course perspective. You can think about it from the regularity perspective.
Oh, absolutely.
There's loads of angles with which you can try to attack the problem. But for me, the main, when it comes to the main question of what are the singularities of a black hole, the actual ones, not the ones in Kerr or Schwarzschild, we just have no idea. Yeah,
fair.
So there's recent work in spherical symmetry where strong cosmic censorship or things like that have been shown, and not fully, but to some extent they have in certain examples. And I think I don't know if there's a consensus, but I think people think, some of the experts working on this, they think that actually the singularity of Schwarzschild is more or less what you expect in spherical symmetry, even in the generic case, like when you just have generic within the class of spherically symmetric, like let's say charged fields or whatever, then people have shown strong cosmic censorship in certain ways. But the best results actually use two-ended initial data, right? But you think that physical data is more like the Oppenheimer Schneider, with just one end and a kind of R equals 0 center of symmetry. So, but in the spinning case, wow, I mean, we just have no idea. So
in Schwarzschild, if you have in some measure a small deviation from sphericity, can you show that you don't get or do get?
No, you can't show anything. As soon as you screw with spherical symmetry, your world changes and the PDEs just totally change because so many more variables are introduced, and suddenly you can't even prove, like, it's very hard. No one has any idea of what singularities might happen when you have something that's slightly deviating from spherical symmetry. Even within a compact set, like even if you just take a small region and screw with the symmetry there, we still don't know.
What about numerically? Do we have any idea?
Yeah, numerically we do. Yeah, numerically there's some amazing results actually, and it shows that actually numerically there's something that happens called critical phenomena, which has very interesting power law behaviors between certain functions, certain types of quantities involving the curvature, involving the density of the field involved, and so we have power law behaviors describing how certain things behave, but probing the nature of the singularity with numerical stuff is also very hard, because when you see numerical things, I mean, I'm not an expert in numerical things, but so far as I can understand, they're very good to understand just about everything you might want to know, apart from where the space-time breaks down, because then you don't know if that breakdown is because of your numerics or because of the breakdown that's actually going on in the space-time. So numerical relativity somehow is great outside of that question we're asking. But on this point, I think numerical stuff has done an amazing job at revealing things that the theoreticians basically no one expected or knew, apart from maybe Christodoulou in his mind, But apart from him, no one had any idea that critical phenomena or any kind of weird behavior would happen, and it was only through numerical that this was understood. And from the theoretical perspective, it's still, we still don't know how to fully account for that or explain that and generalize that to more general situations. So yeah.
Thank you.
Are there any further questions?
So I have a question for Dan. I don't know if he's still here, but
I am, yes.
Yeah. So
Thanks.
I mean, a question for Juliusz and for Dan, but Dan, so you're saying, so right. So Juliusz is saying we'd like to see if QFTs can be defined or can be worked on and worked with on non-globally hyperbolic spacetimes. Dan, I know, of course, that you looked at this right in your master's thesis, and maybe you're still looking at this. But you're saying that actually, existence is not such a big deal. The big deal is whether or not you can show the Hadamard states, that these Hadamard states exist.
Yeah, so, I mean, on a technical level, you can just construct an algebra by saying, oh, I only I construct your theory by only imposing commutation relations to hold locally, and in principle, this gives you an algebra and this gives you a quantum field theory that is F local. But whether such a theory has any physical significance is then well,
right. But so what's the sure? But now what's the issue? The issue is that when you have when you try to prove the existence of these good states, you're saying that you need to know more about the geometry, and that turns into a problem of solving the semi-classical Einstein equation to some extent.
Well, I mean,
what exactly did you mean by that? Like, how far are we to understanding what
what you would need is a better understanding of how Hadamard states evolve on on spacetimes, and in particular, what happens to Hadamard states and what happens to observables like the stress energy tensor as you approach the Cauchy horizon of a spacetime, of a globally hyperbolic spacetime.
So when you're saying dynamics of these things, are you saying the semi-classical Einstein?
No, I'm just saying some fixed background spacetime, and for instance, like let's say the bottom half of a evaporating black hole spacetime, which is globally hyperbolic, and just put a quantum field theory on there and see how the states of that quantum field theory evolve.
So let me ask you this. This is why now I get to the point. When people do strong cosmic censorship, say, they take, for instance, the Fermat's Luke, right, which is kind of the most up-to-date thing you can do in terms of rotation. Now, in a lot of this work, a lot of the mathematics behind that was about understanding the behavior of waves or other types of fields on a fixed background as a kind of like first step to understanding the Einstein equations. You study a fixed background and you study waves, the wave equation on this background, and you track the properties of fields as they approach the Cauchy horizon, singularities, and so on and so on and so forth. So there is a good bit of literature on, what happens to scalar fields, what happens to Klein-Gordon's fields, what happens to massless fields in the context of non-globally hyperbolic spacetimes. Because of strong cosmic censorship, people have asked, how do these fields behave on approach of a Cauchy horizon, etc.
Yeah, and that also. Oh, sorry.
So then my question is, do you know this literature? Does this literature help at all to solve your problem? Is there a radically different thing happening that we can forget about this literature? Like, what's your take on that?
So I will say that I don't know it very well, but what I do know is that lots of these are concerned with, say, the inner Cauchy horizon of a Kerr or of a charged black hole. And there, it is actually interesting because if you do indeed consider these quantum field theories on that spacetime, then you, at least from numerical simulations, it also seems to be that this Hadamard states cannot be extended beyond this Cauchy horizon. So that's a work by Stefan Hollands and Robert Wald and others. But that does sort of rely on this Penrose idea of how cosmic censorship of how blue shifts of.
But do they have a theorem, or is it like they do investigations?
They do investigations. There are no theorems as far as I know, at least. The most recent thing that I saw Stefan do on this was more numerical studies. But the question is, the Cauchy horizon of a black hole evaporation spacetime is a very different Cauchy horizon, in a sense, and there's not really this blue shift of incoming modes in the same sense that you have in Kerr black holes, for instance.
Absolutely.
So, in that sense, I don't know if this literature can be sort of taken over to this case.
Yeah, then there's a hard case of the rotating evaporating black hole.
Yeah, well, that's a whole other case. I must admit that I've only mostly focused on spherically symmetric cases.
Of course.
Yeah, the question is already hard enough because we don't really know how Hadamard states generically. Well, we have general theorems about how the singularities of those states propagate. So the singularities of the 2-point functions, but what they really do and where, and what you can say about their extendability beyond certain globally hyperbolic regions. Yeah, we don't know much about that as far as I'm aware.
What's the difficulty in the spherical symmetric evaporation? Like what's going on? So in the blue shift, instability, you can see the blue shift on a Penrose diagram. You can see something will go wrong.
Well,
So,
the difficulty is that you don't really know what the geometry of the evaporating black hole spacetime is. You just have a sort of causal structure by a Penrose diagram, which is even a bit hypothetical because no one has actually solved any semi-classical Einstein equations. And
so that's why I ask, because there's actually a paper of Todd where in the 90s with someone else where they actually take like they construct a solution which kind of resembles an evaporating black hole because the mass that's decreasing, it's spherically symmetric, and they don't have a full geometry. But I think that's why I'm asking, is because actually some geometries have been constructed. They're not widely known, and they're not particularly expected to hold generically or whatever. But I think it could be interesting to look at.
Yeah, I must admit that I've been planning to look at this a little bit more, but right now I'm working on a more general view of how Hadamard states evolve along characteristic surfaces as you evolve them. So in that sense, you might want to see what happens if that characteristic surface approaches a Cauchy horizon, or rather the sort of naked singularity there. But this is ongoing work.
Well, it sounds very exciting.
I hope so. We'll see if it actually gives you something.
Thank you.
Are there any further questions?
Jamie and Martin, could you hang on after the call just for a moment? Juliusz, thank you. It was really a lovely talk and very good discussion.
Thank you all. It was, super fun for me, and I've learned a lot from you folks. Thank you so much.
Thank you again.
Bye, Juliusz. Thank you very much.
Cheers.